we are going to look at the I-format instructions. So I-format instructions are basically the instructions that have, or most of them, that have a constant number. So if you look at the example here, we are doing an or I, and we are passing two registers, and we have a fixed number as a third argument. So this is the I-format instruction. Basically, I think the most common one that we've seen in the previous weeks is basically the add I. That we said we had two instructions for add. We had add and we had add I. So add was, so if you put, for example, here S0, S1, S2. So this was basically S0 is equal to S1 plus S2. So this was basically adding two registers, so these two, and then saving the result in S0. But add I was something like that. We give, that's a destination register, so we're gonna save the answer. And then we had S1, and then you could give it a number. So for example, 56. So then your result would be S0 is equal to S1 plus 56. So that was the add I. So if you just think about how, like if you were going to design basically these patterns or different instructions, so when you have this number 56, for sure you need to store this number. And that's when this I format comes. So in this case, we had to only store three registers, and also we had to store the type of the instruction. So here, so that was the R format, and there is the I format. So here we are still, we have to register basically or save into that 32 bits that we have the type of the instruction. So we have to somehow tell the CPU, or the CPU should somehow find out that this is an add I instruction. So we need that. We still have the two registers, but this time we are storing a number instead of the third register. So the way this works is that the pattern that we have is basically we have the operation code. So this is going to be 6 bits. And then maybe I write it up here. And then we have two spaces for the registers, and each is going to be 5. And then we have 16 bits for the I. So this number that we are putting here, that is maximum can be 16 bits. So, and you can find out what is the maximum number with 16 bits. Basically, if you have something like that. So that's a binary number. So that would be the maximum value that you can basically store here. Or maybe it's actually 2 complements. So maybe this would be 0. So one of them is a sign. But basically you have 16-bit space that you can put that number there. So let's look at more examples. So here, don't let the notation confuses you, is basically trying to explain these each instruction. So for example, if you are doing an add I, we have 2 registers and we have an I. So I is a 16-bit immediate or 16-bit constant number. So how this going to be working? Basically RT, which is the first one, so that's kind of like the same as previous what we've seen, is going to be RS plus I. So nothing new. The only thing is that this I is, we are giving the 16-bit. When you are doing an add, so this is a 32-bit number. This is going to be sign extended for 32 bits. Because you don't want to basically change the sign. So if you had 32 bits number here, so this is a 32 bits number, and then your other number is maybe like 16-bit only, so it's only like that. And if these two are two complements, so if this is 2C and this is 2C, so both of them are two complement, if you're adding them like this, it could mess up the sign, because you might have a 1 here, and that is showing this is a negative number, and you have a 1 here, that is a negative number also. But if you add them, basically we're gonna lose that whole concept that we talked about, that the sign gonna take care of itself. So how we solve that? First, we have to sign extend this. So we're gonna sign extend this all the way. So we get a 1 there. And then if you add them, the sign basically gonna take care of itself. So you shouldn't worry about changing the sign. But that's just a detail. The important thing is here, because we have 16 bits only here, we have to sign extend and then add. And we're gonna see this limitation more in the next slides. So there is another one that we have. We have an AND. So we have basically, this is going to be the result, and you're doing an AND between this and that. So these two arguments, we are doing an AND operation. So this notation here that you see here is basically means we are concatenating these two things. And this here is basically means 16 zeros. So you have 0, basically 16 times repeated. So this is just the notation that is used in these slides. I don't think it's any universal notation. So how this gonna be working? You're doing an AND between basically one number that could be 32 bits and 16 bit. So this is going to be only 16 bits. So this is going to be shorter than that. And when you are doing an AND, these are considered to be zeros. So basically you get rid of that part completely. So the first 32 bit of your number is going to be 16 zeros. And then the second 32 bit, or the lower bits, is going to be the result of the AND between this I that you are giving to this number and the lower 16 bits of this register. So that is going to be, so for example, if you had, let's say, this RS was all ones, so you had 4, so I'm going to put one line for each 4, so that's 8, 12, 16, and then 4 more. So 1, 2, 3, 4, 1, 2, 3, 4. So that's like 6. It is ones. So if that is your number, if that is your RS, and then you're doing and with all ones, so this is gonna be ones also. For basically this part is ignored. So the higher 16 bits is completely ignored, and your answer is going to be zeros all the way for 16 bits. And then the lower 16 bit here is going to be the result of this AND. So these ones, for example, if we have 1, 1, 0, 0, 0, 0, 1, 1, here we're gonna get ANDing each bit. So 1 and 0 is a 0, 1 and 0 is a 0, 1 and 1 is a 1, 1 and 1 is a 1. So basically each two number is going to be an AND operation, and we're gonna get the result down here. So that's basically how it works. The OR operation, it's basically pretty similar. So here we are gonna get, because we are doing an OR, it just changes in that higher 16 bit. So here we had 16 zeros at the high part because we didn't have anything on the number itself. But when you do an OR, so for example, if you have, let's say, I can write it here. If you have, let's say, 1, 0, and, or let me put it in this way. I'm going to if you have a 1, they have basically 4 cases. If you have 1, and then if you have 1, 0, 0. So if you have a 1, doing an OR with 1, so 1 OR with 1, you're gonna get 1. If you do with a 0, you're still gonna get 1. If you here again, doing this one with a 1, you are going to get 1. If you are doing this one with a 0, you're gonna get 0. So what you can see here is that whenever you have a 1, you're gonna get 1 always. But interesting thing here is that whenever you have a 0, so whenever you are doing an AND with a 0, you can think of it in a different. So right now, if I tell you, let's say you are doing an AND with a 0, what is the answer? So your mindset, it's probably that depending on the other one. If the other one is 1, we're gonna get a 1. If the other one is a 0, like here, we're gonna get a 0. But I want you to think in a different mindset that if you are doing a OR with any, like if you're doing an OR with a 0, so something or 0, you're gonna get something as an answer. So you're gonna get that original number as the answer. So for example, if I say x or 0 is equal to bx. So basically that is what I mean. So basically this or 0 is something that you can just remove. Because always if you OR anything with 0, you're gonna get the original number. So here we are doing an OR between this number, that is a 32-bit number, so RS is 32 bits, and I is 16 bits. So if I put like that, so each line is 4 bits. So this 16 bits going to be here. And how it works, it basically gonna assume these are all zeros for the second one. And we are going to get the same thing here as the answer for the higher 16 bits. So what we have here. So higher 16 bits of the RS is going to be the answer for the higher 16 bits. And then for the lower 16 bits, we basically gonna get the odd result of this. Basically RI and the lower 16 bit of this RS. So the XOR is basically the same thing. We are getting the higher 16 bits of the RS. So that is being basically unchanged because it's all zeros. And we are getting the lower 16 bit. We're gonna do a XOR between these two numbers. Okay.